Good day to Doctor and all my fellow friends. I am Yeoh Jun Yun, the presenter from Group 4. Today, I would like to present about the application of linear algebra to genetics. First and foremost, let me ask one question regarding what is meant by genetics. To understand genetics, we need to know a biological terminology known as genes. According to Mendelian inheritance, the genes that are passed from parents to children determine the inherited traits such as some physical characteristics, natural talents, and genetic disorders. A trait may not be observable, but its gene can be passed to the next generation. In short, genetics is the study of heredity of these genes. Then, how is linear algebra applied in genetics? In particular, linear algebra is widely applied in population genetics, which is the branch of genetics that explains how transmission of genes changes from one generation to another. The integration of both science of genetics and linear algebra provides useful tools that can predict our future based upon our genetic makeup. For instance, linear algebra can be used to predict the genotype distribution of a particular trait in a population after any number of generations. In our example, some algebra concepts such as converting linear equation into augmented matrix and performing matrix multiplication are used. Let us move into our example. In a certain animal population, an autosomal model of inheritance controls eye coloration. Typically, there are two different forms of genes denoted by A and A. Each individual in a population carries a pair of genes called the individual's genotype, but each heritable trait is governed by a single gene. This gives three possible genotypes for each inheritable trait, such as AA, AA, and AA. Genotypes AA and AA have brown eyes, while genotype AA has blue eyes. Genotypes AA and AA are indistinguishable in appearance because the A gene is said to dominate the A gene. Given the genotypes of the parents, we can determine the probabilities of the genotype of the offspring. Suppose that in this animal population, the initial distribution of genotypes is given by AA equals to Y1, AA equals to Y2, and AA equals to Y3 with equal probability 1/3 for each of them. Hence, the converted 3 times 1 matrix is shown as below. Our objective is to determine the probabilities of the genotype of the offspring in n generation if keep crossing offspring with dominant animals AA only. In each of these cases, let's figure out the probabilities of the offspring being AA, AA, or AA. First, consider the crossing of AA with AA. Since the offspring will have one gene from each parent, it will be of type AA. Thus, the probabilities of AA, AA, and AA resulting are 1, 0, and 0 respectively. All offspring have brown eyes. Next, consider the crossing of AA with AA. Taking one gene from each parent, we have the possibilities of AA, 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 and AA. Thus, the probabilities of AA, AA, and AA respectively are 1/2, 1/2, and 0. All offspring again have brown eyes. Third, remains to consider the crossing of genotype of AA with AA. There is only a possibility, namely AA. Thus, the probabilities of AA, AA, and AA are 0, 1, and 0 respectively. No offspring have blue eyes. Our next step is to examine how the above fractions of initial genotypes will change from one generation to another. For this, we let Xn be the distribution vector of genotypes in the n generation. In the first generation, the fractions of genotypes AA, AA, and AA can be expressed as linear equations below. This is actually a linear system of 3 equations in the 3 unknowns Y1, Y2, and Y3. Hence, the system can also be written as matrix in the form of x1 equals to ax0, where shown in this slide. To find x1, which is the fractions of genotypes in the first generation, we perform the matrix multiplication between matrix A and x0 with y1, y2, and y3 equals to 1/3 for the initial fractions of genotypes x0. In the second generation, we also carry out the same procedure except the x0 is now replaced by x1 or x2 equals to ax1. This is the same for the n generations. As a result, the general form of matrix for this example will be x1 equals to ax n minus 1. Explicitly, we have the calculation as shown here. So, what other conclusion can be made from the result? It is obvious that this sequence of vectors converges to the vector x equals to 1, 0, and 0. In conclusion, the AA type become a larger and larger fraction in each successive generation, contrasting to AA type that becomes a smaller and smaller fraction. The AA type disappears after the initial generation. Eventually, you will see that the offspring will only have brown eyes in this model for crossing offspring with a dominant animal. This is one of the examples of how linear algebra can apply to genetics. At the end of this video, we can also try to create a similar model for crossing offspring with hybrid animal AA or a recessive animal AA by using genetic algebra. This is also applicable to other inheritance traits for humans like hair, skin color, blood type, and more. That's all from our group. Thank you for listening.